In this video, we're going to do some practice problems revolving around contour diagrams of functions of two variables. So our first example is one that we looked at in section 8.1, looking at the profit of a store that sells two things, xylophones and yo-yos. Xylophones represented by X, the number sold. Y is going to represent the number of yo-yos sold. And we were given this as a table of values, the first thing we kind of learned about with functions of two variables. So note that if the store sold 20 yo-yos and 10 xylophones, the profit would be $180. And in that video, we looked and found that the profit function could be written out algebraically as P of xy equals 10x plus 4y, looking at cross sections of this in just the terms of x and y, where either one was set equal to 0. So now let's think about this in terms of contours. First one, we're going to find the contour for P equals 200 algebraically. So what that means is we are going to set exactly P equals 200. So that is going to be 10x plus 4y equals 200. And that is a line. We could leave it like that. If you're so inclined, you could put that into slope-intercept form. 4y equals negative 10x plus 200. You could divide by 4 there. You would get a negative 5/2 x plus 50. So the slope would be negative 5/2, the y-intercept would be 50, and you could look at that as just a line, and we'll see that on the next page. Note that this is a perfectly acceptable answer algebraically for that contour. Thinking about where this is in the table, where would that contour be? Now, it's kind of weird to think about it in the table, but let's see that we know some values of exactly 200. And then we can say that 200 is going to be kind of in between these values. So maybe we have something like this. There's no really right way to kind of draw this contour in a table, but we know that everything to the left of that line is going to be less than 200. So everything over here is going to be less than 200. Everything to the right of that line is going to be greater than 200. So that's something we could see with the table of this kind of contour. And it sort of gives us this idea of some line here in the table. All right, now let's graph the contours for P equals 100, 200, 300, 400, and 500. And again, these are all going to be the lines 10x plus 4y equals 100. We're going to set it equal to 200, which we already did, 300, 400, 500. And I urge you to maybe stop the video and try this on your own to try to graph these contours before we look at the result on the next page. So here we go. This is going to be a graph of these contours, and this represents here, this first one is going to be our 100 line. The next one's going to be our 200, then our 300, our 400, and then our last one is 500. So again, the contour lines, the actual lines are going to represent the profit. Here is going to be our X values. Up here is going to be our Y values. And given this diagram, we can get some information where we're going. We can see that, first of all, this line, this blue line was our line that we found before, y equals negative 5/2 x plus 50. It has a y-intercept of 50 and a slope of negative 5/2. It is exactly those kind of lines that we're looking at here. From this picture, we can get a lot of information about what's going on. So we know that as x increases, we know that the profit is going to increase as well. As we kind of go from left to right in this picture, we are going from smaller contours to bigger contours. Remember, this first one is 100. This last one is 500. And we could say the same thing for y as well. As y increases, P is also going to increase. That's looking as we go kind of up this diagram. We go from low contours to high contours. And that should make sense in this problem. If you sell more things, you should have more profit that kind of comes in, more revenue. And again, in this represents, these lines represent all the points that have a certain value. So again, this green line represents profit of 300. So if you sell, let's say that you sold 20 xylophones, you could figure out exactly how many yo-yos you would need to sell to get to exactly 300. And that would look like maybe about 25 in that picture, right? Corresponding to that point, 2025 on that contour. All right, let's look at another example. This is going to be kind of completely different from that one. So this contour diagram shows happiness, that's going to be the actual function itself, on a scale from 1 to 10, as a function of love on a scale of 1 to 10 in someone's life. So this is love from a scale of 1 to 10, and then money in some kind of scale. So the idea is that if you have a certain amount of love in your life and a certain amount of money, you have a certain amount of happiness corresponding to that. So describe in words happiness as a function of money with fixed love and love with fixed money. This is our idea of a cross section. If you just fix one of the variables, what would happen to the other? And this is often what we're going to be doing to try to understand these functions of two variables. And it's really difficult to see the two things changing at once. But if we think about just what happens if I have a fixed love, what happens with money, and vice versa, we can understand this a little bit better. So, first thing is, what happens to happiness as a function of money? So here we're thinking about what happens to this happiness as I'm going up this graph. And we can kind of see that the happiness is going to increase, right? As we kind of go here, happiness is increasing. But then as we go a little bit further, the happiness starts to decrease, right? So at a certain amount of money, your happiness can increase, but at a certain point, it's not going to matter how much money you have. And in fact, your happiness may decrease depending on that, at least according to this example. Then let's do the same thing with a function of love with fixed money. So that is, we're going to be going across the x-axis in some capacity. And if we see that, the happiness only increases that whole time. So the more love you have, the more happiness you have, and there's nothing really more to that. At a certain point, you kind of have a max happiness of 10. Doesn't matter how much love you have. All right, so now let's think about this specifically. Graph two different cross sections with love fixed and two different cross sections with money fixed. This is something we kind of already did in this example, but we'll do it again here. So first, let's do it with love fixed. Let's think about if we had a love value of, let's say, 5. And we're looking at this cross section, and we're trying to kind of figure out what's going on with that. What happens when money is changing with that love? If we kind of think about this, we know that the happiness is going to increase and then start to decrease at a certain money value. So this is going to look like, you think about love and happiness, this function is going to look something like this. Oops, sorry, that's not love and happiness, that is money and happiness when love is equal to 5. And you might have a different sort of thing if you had a different cross section here. Maybe if we had love equals 10. Right, you might have a kind of a bigger curve and it flattens out there just because we have a max happiness we can have. Let's do the same thing with fixed money now. We'll do the easiest one, some kind of money value here. We can see that the happiness is just going to kind of increase at a constant rate or a little bit more constant whereas opposed to maybe low money, so if we kind of put this on the same axes here, we have a function of love, happiness, we have different monies here. We can see maybe the first one is kind of increasing at a constant rate. Happiness is always going to be at least kind of greater than or equal to 4. And then the other one, happiness is often a lot less, right, but still kind of goes up a little bit, but at a less rate. So those are kind of both those graphed on the same axes. This is a very vague example, so we don't really have specific things. But again, thinking about a much different sort of application of these functions of two variables. So another example here. This is a specific function we're given. Use the contour diagram for this function to answer the following questions. So these are given our contour diagrams. We have 0, -2, 2, 4, and 6. Note that we do have intersecting lines here, but that is okay since they are the same value, right? They both have zeros there, so that's okay if the same contour line intersects each other, but not different ones. All right, so first question, find f of 1, -1. So that is, we're going to have x be 1, we're going to have y be -1. That corresponds to this point right there. And that's going to give us a value of 0 because we're on that contour line labeled 0. Let's do the same thing for f of 2. So that is x is 2, y again is -1. That's going to be at this point right here. And if we kind of follow this contour line along to get to the label, we can see this has a label of 4. That is the contour corresponding to 4 in that picture. Let's find f of -1, 0. So this time x is -1, y is 0. Corresponds to that point. If you kind of follow the contour along to find the value, that'll give us a 2. So now let's switch up the question a little bit. Let's find a value of x for which f of x -1 is equal to 2. So here we're looking at maybe a cross section where y is fixed to be -1. So we're looking at this cross section here. And is there an x value for which we have a function value of 2? And there are a few options here. We know that this is going to be a value. I just covered up the 2 right there. That's going to be a value. We also are going to have a value here is going to be a 2. And that should be about it. One more. That's also going to be a 2. So any of those would be fine. Maybe a -1.75. 0 is a very good one right there. And then maybe positive 1.75. Any of those would be fine. I think 0 is the answer that we're looking for the best because it works out best there. Let's do the same thing. Find a value of x for which f of x2 equals 0. That is looking at a different cross section where y is fixed to be 2. And this time we're looking for that equal to 0. And there are, again, a couple of options here corresponding to the different values of 0 in this picture. So maybe some answers there would be a x is equal to -2 and an x is equal to 1 would be both okay there. And let's do the same thing with cross sections in the other direction now. So let's look at a cross section, find a value of y for which f of 1y equals 4. That means that x is fixed to be 1. And we want to find a value for which that is equal to 4. There seems to be only one option here, and that is going to be up there. So x is 1. What is the y value that gives us an x equal to 4? That's going to be a little bit more than 2, maybe 2.25 about. And lastly, find a value of y for which f of 0, y equals 0. Again, that is looking when x is equal to 0. So that cross section, our answer has to be on that line. And we can see kind of right in the middle would be an answer. So x is equal to, or sorry, y is equal to 0 in that case. Maybe a good exercise to kind of see about what does this actually look like, this picture, because it's an interesting picture to examine. We see that the elevation is increasing over here. There's like a little hill. It's going down over here. It's like a little valley. And then we're going uphill to the right. We're going downhill to the left and the bottom. Just an interesting kind of picture to see about this function. So one more example here. So antibiotics can be toxic in large doses. If repeated doses of an antibiotic are to be given, the rate at which the medicine is excreted through the kidneys should be monitored by a physician. So one measure of kidney function is the glomerular filtration rate, or better said, GFR. I've never had to say this word before in my life. This measures the amount of material crossing the outer membrane of the kidney in milliliters per minute. A normal GFR is about 125 milliliters per minute. The figure below gives a contour diagram of the percent P of a dose of an antibiotic excreted as a function of the patient's GFR and the time T in hours since the dose was administered. So, what does this graph represent? Notice that all of these GFRs are less than normal. So this is people with some kind of kidney issue, right? Their GFR is not normal, which means that the amount of medicine that's excreted through the kidneys is not normal. So we're looking at that in GFR, and then we're going to think about when the antibiotic is given, what happens to the percent of that antibiotic in the system after a certain amount of hours. So on the next page, we're going to answer some questions about that. First question, in a patient with a GFR of 50, approximately how long will it take for 30% of the dose to be excreted? So note that the 30% here is going to correspond to this P equals 30 contour line, as that's what we're looking at here, is the contour represents the percent of the dose to be excreted. And we are looking at a cross section here of GFR equal to 50. So we have this contour. Now we're asking, when does that contour intersect with the line P equals 30? And that's going to be at 4 hours. So it would take 4 hours to get to that percent level. Let's do this again. In a patient with a GFR of 60, so this time we're looking at a different cross section here, approximately what percent of the dose has been excreted after 5 hours? So now we're also just looking at 5 hours. Where do those two lines intersect? And that's going to be on the line P equals 40 or 40%. Okay, that's basically what is the function value. This is what is P of 560. The time is 5, the GFR is 60. What is that percent? All right, so from the graph, explain how we can see that a patient with a fixed GFR, so their GFR is not changing, the amount excreted changes very little after 12 hours. So from the graph, we can see that if we look at 12 hours onward, the graphs, these lines are all pretty much flat, which means that with a constant GFR, your percent won't change. Let's look at maybe just one example of that. Let's say you had a GFR of 20, and after 12 hours, the percent that you're going to have is basically unchanged. Everything that's already happened with that drug has already happened. Nothing else is really going to change after 12 hours. And that should make a little bit of sense, right? After a certain amount of time, the effect of something is going to wear off, or it's not going to be nearly as much as we go forward. All right, and then some final questions. Is the percent excreted an increasing or decreasing function of time? So as we go from left to right in time, what is happening to the values of P? And we can see that as we go from left to right, let's just even pick just one of these cross sections. We can see that the percent excreted is increasing as we go on. Right? We're looking at the percent of the drug that's being excreted. We start at 0% excretion, and as we go forward, it's going to excrete more and more of that drug. And then, is the percent excreted an increasing or decreasing function of GFR? So this time we're looking at if GFR is going up, what's happening to the percent? If we look at maybe just some cross section here, we can see that this is going to be increasing as well. So let's answer one final question. Explain what this means to a physician giving antibiotics to a patient with kidney disease. This graph represents something with everybody has a kidney disease, as the GFRs are all below zero, or all below normal, 125. So if we give an antibiotic with somebody with this, we can see that the percent that's going to be excreted is always going to be less than ideal, less than kind of 100%. But we can see that with a higher GFR, more of the drug is going to be excreted than if we have a less GFR. And that's what we just mean by this being an increasing function. There are a lot more examples we're going to look at in the homework in terms of contour diagrams, and then we're going to start looking at functions of two variables in other ways in the next few sections.